Hi everyone, this is Michael Lee. Today I'll be talking about some of my work on interpretable matrix completion. This is joint work with my advisor, Professor Dimitri Persimas, and I would like to thank the committee for selecting this poster to be an MIP finalist poster. First of all, some introduction into matrix completion. Matrix completion is a problem in which we're trying to fill a partially filled matrix using the low rank assumption. The general matrix completion problem with rank K can be formulated as follows, where we have the loss between the fitted matrix and the observed matrix A, plus some regularization term subject to the low rank constraint. Now, in most common matrix completion applications, the rows are some users and the columns are some products. And in this, it offers a very intuitive interpretation of the low rank assumption. Matrix completion is essentially trying to find K product features in which K is very small, such that the response for each person I is a linear combination of such features. And thus what it's really saying is that there's only really a very small number of important features, and those are B1 to Bk. And thus a very natural question is that to ask, what are those features? However, this particular formulation, in which is the general form of the matrix completion formulation, does not offer us any insight because V is completely unconstrained. So we introduce a new formulation. We call it interpretable matrix completion. Let us introduce B, the matrix which is a collection of P interpretable product features. And we will stipulate that the columns of V have to be selected from V, so that the features that appear in the V are also interpretable. And such features in the matrix B might be, example for movies, might be running time, might be IMDb score, might be budget, etc., etc. Then the problem of matrix completion subject to such constraint can be formulated as follows, where S is a diagonal matrix formed of binary variables from S1 to SP, in which the sum of them is K to ensure that the rank is still K. And in this paper, we particularly take this problem with the Tikhonov regularization term, which is the L2 squared norm, to induce robustness. So now we have this problem. How do we solve it? Well, first we substitute the condition in, and then we see that this inner minimization problem is really a weighted rich regression problem, where Aij is the response, Bkj are the design matrix, and Uik are the coefficients. And thus it can be solved easily in closed form, in which the final solution is as follows, with the appropriate matrices as defined below. Now, with this particular form, we can see that this is a convex function of the binary variables Si that select the particular features from B. The reason that it is convex is because the inverse of a positive definite matrix is convex, and inside the inverse, we see that it's a linear function of S. Since it is a convex function of binary variables, this minimization problem is amenable to the cutting plane method. But there's one problem. Generating each cutting plane requires evaluation of the value of the derivative. And this in turn requires n times p plus k squared plus nk cubed complexity. In particular, it requires linear dependence on both n and n. In real life problems, matrix completion problems often scale up to hundreds of thousands of users and thousands, if not hundreds of thousands of products. And thus, generating a full cutting plane is computationally infeasible. How can we make it faster? The insight is that this value, C of S, this cost function, appears to be some kind of average across the rows and columns. We have this 1 over n term here that appears before the sum. So we will try to utilize sampling to approximate the value of C of S and nabla C of S, the derivative. Now, the objective value can be written in this following form, where we have moved the 1 over n term inside. Essentially, this inner term is the average objective loss we have for one row across all the columns. And thus what we're going to do is that we're going to call it alpha IFS, and then we're going to approximate the value by averaging over instead of F columns, where F is a random sample taken without replacement. And now we can approximate the true cost function with this approximated value. But now we see that the outer sum is also 1 over n over a summation form. It's also a form of the average. So we do a second layer of approximation by, instead of averaging over all n rows, we choose a random sample again of g rows to formulate our cost. And we can similarly do so for the derivative. The problem is this approximation good? And it turns out if we are careful with how we do our sampling, then those approximations are indeed good. Specifically, we need to sample the rows first, and for each row, sample an independent sample of the columns. And under such condition, then with high probability, our estimate of the cost function and its derivative is very close to the true value. Now, armed with this, we can now introduce our full algorithm OptComplete. We first start with a random initialized point as 0. Then we calculate the approximate value and the derivative using the previous approximations. Then we solve the cutting plane problem. But instead of using the true cutting plane, we use the approximated cutting plane as illustrated above. Then we repeat this process until we terminate, which is when our solution doesn't update anymore. So this is our whole algorithm, which is exactly the same as a cutting plane algorithm, except we're not using the true cutting plane. But this gives us one problem. Does it actually converge to the optimal solution? And it turns out because our approximations are good, it does. So formally, for this interpretable matrix completion problem, we have that the OptComplete algorithm terminates in a finite number of steps, and more importantly, finds an optimal solution with extremely high probability that is exponentially decaying in the number of rows selected. Note this does not depend on the number of columns selected, and only depends on G. And with this, we can know that if we select the reasonable amount of G, then we'll have a high probability that this algorithm will work. And so with this, we will now select F and G. We know that the failure probability decreases exponentially with G. And from Candace and Tal, we know the minimum number of elements needed for a unique solution for the matrix completion problem. And thus, we need to at least select that many rows and columns so that we have a unique solution to our problem. And thus, F times G needs to be on that order of magnitude as Candace and Tal pointed out. And we're going to maximize G subject to that constraint to minimize our failure probability. This results in the following F and G expressions. And this allows OptComplete to scale with a computational complexity of square root of nm log nm. Compared to the original n times n, this is a much needed increase. Now we will show our results on the real world experiment. We tested our algorithm on the Netflix problem, in which we have movie ratings of up to 450,000 users and 18,000 movies, of which only 5% of the pairs are filled. And our goal is to predict ratings of user movie pairs that are not present. We collected over 50 features for each movie to formulate the B matrix. And then we randomly withheld 20% of the known ratings and utilized OptComplete to predict such withheld ratings using the features that we collected from B. Now, because this is a new formulation of matrix completion, as far as the authors know, we do not have true comparative algorithms. And thus we compare it to inductive matrix completion, which is also a form of trying to utilize side information into matrix completion. And also we're also going to compare to soft impute, which is well regarded as an extremely fast benchmark for general matrix completion. And here are the results. We see that across the board, OptComplete performs very favorably in time and mean average percentage error out of sample. In particular, in the largest instances, OptComplete is 20 times faster than IMC and soft impute and shows very good scaling behavior. And this is very impressive because this means that for the entire Netflix problem, OptComplete can solve it in under 4 minutes, and with a lower error than both IMC and the general matrix completion algorithm soft impute. Furthermore, OptComplete can give us insights where IMC and soft impute can't. OptComplete recovered that the following features were the most important: IMDb rating, genre, if the genre was drama or not, if it was released within the last 10 years, the number of top 100 actors, and whether or not it was produced in the US. And this gives decision makers valuable insights to understand user behavior. So in conclusion, we introduced the concept of interpretable matrix completion and developed OptComplete, an algorithm based on the novel idea of stochastic cutting planes. Real-world experiments show that our algorithm match or exceed other state-of-the-art algorithms for matrix completion. And furthermore, it really allows interpretable insights for decision makers. And third, the idea of stochastic cutting planes, of not using all of the data at each given point in time for the cutting plane algorithm, is general and can be applied to any strongly convex problem in integer space, for example, sparse regression. Thank you.